Alrighty, so for our second part of the experimental design notes, my original recording did not save as anticipated, so I'm recording it from a different location, but this should help explain for any of those who are watching the video later. So we've talked about the first two experimental designs, which was completely randomized and the randomized block. If you need to see the notes or the videos on that, please watch the previous recording. For this one, we're going to start with matched pairs. It's a special type of block design in your experiments, which has two different methods. The first method is where you match up experimental units according to similar characteristics. And then within those groups of two, because everybody's going to get matched up with who they're most similar with, you would randomly assign one of your treatments to one person, and then the other would automatically get the second treatment. So basically, I would walk up to two people who are similar and say, you guys are going to work together. You're both the same height, same age, same gender, whatever. You guys are going to work together. And then I'd flip a coin basically and say, okay, you're going to get experiment number 2 because it came up tails, and you're going to get the other experiment. And then my randomization process would be assigning them the actual treatment randomly, either option 1 or option 2. For the second method down here, what I would do instead of matching people up is I would just take the individual experimental units, the rabbits, the people, or whatever, and I would split them, or not necessarily split them, but I would assign to that individual unit both treatments at a random order. This is similar to kind of what we would see, I'll explain this a little bit more, like a taste test where we would let the one individual would drink both mystery cups of soda and then tell us which one they like better. So they're doing both experiments, or they're doing both treatments, I should say, but they're doing it in a random order. So the randomization then becomes which order they do the treatments in, not which treatment they get. The assignment of treatment is, and it says this in your note, is dependent. So it's going to be, dependent on the characteristics, how I flip the coin, all that stuff. All right, so here's an example of method number 1. I've got all these little faces down here at the bottom, and they have similar characteristics. Some are smiling, some are frowning, some are neutral, some are green, and some are red. So what I would want to do is pair the experimental units according to their specific characteristics. So this is using option number 1, where I can find a pair of unique people or experimental units and put them together. So I'm going to go ahead and do that. So all the green smileys go with the green smileys, the red frownies go with the red frownies, et cetera, et cetera. And now all of these experimental units are matched with somebody that they're very similar to. And then from each of these groups of 2, I would randomly split them into treatment A or treatment B. So now that I have them all matched up with who they're the most similar to, randomly assign one of them to do treatment A and randomly assign the other one to do treatment B. So we're going to go ahead and do that. So the frownies get split up, the smileys get split up, the greens get split up, and the reds get split up. And so now what I have is a guarantee that in treatment A, one of the unique characteristics will be doing that treatment, and in treatment B, one of the unique characteristics will be doing that one. So we have a green frowny guy on both treatments. So now it's not dependent on the person's characteristics that are determining the outcome of the experiment. Now the treatment itself is the only thing that's being measured, because each treatment is having an opportunity to be tried on every different characteristic. So this is another way to help with those confounding variables and splitting it up. The second method is like doing a taste test, like I kind of said earlier. So I would take just the green frowny guy and say, hey, you're going to do both treatment A and treatment B, but you're going to do them in a random order. And then I would take this green frowny guy and say, hey, you're also going to do treatment A and treatment B, and you're going to do them in a random order. And so now the individual units are doing both treatments, whereas with method 1, they're only doing one or the other because they were matched up first. So this is both examples of matched pairs. So if you're not quite sure, make sure you ask me in class during our time, and I will try to clear this up a little bit better. Matched pair is definitely the more confusing of the 3 types that we deal with in our experimental design. So let's go through a couple more examples that are on the back pages of your notes. So we have Miss Yasmin, who owns an exercise studio, and she's curious to know whether yoga or kickboxing helps you relieve more stress. She recently had 20 new people sign up for an introductory 6-week course in yoga, and 20 people also sign up for an introductory 6-week course in kickboxing. She then measured their stress level before and after the 6-week course for all of the participants, and she noticed that the participants who took the kickboxing course showed a significantly higher stress level decrease than those in the yoga course. So after all this was said and done, she saw that the kickboxing people were able to reduce their stress much more than those in the yoga class. So question number 1, or letter A here, what is the explanatory and response variable for this situation. So when we're looking at the explanatory variable, basically, what are we using to explain the possible response that we're going to measure? So we know we're going to be measuring stress levels, so that's a response variable. And what's going to determine the level of stress in this case is going to be the type of course that they chose. So they're going to have more or less stress, according to this example, if they did yoga versus kickboxing. Now, here's the big question of the day, though. Does this actual example here prove that kickboxing is better at relieving stress than yoga? And the answer to that is no, because we have to remember, in order for an experiment to be valid, in order to actually show causation between something of an explanatory type and causing its response, in order for A to make B happen, we would have to be randomly assigning treatments to people. So because she allowed people to kind of self-select which course they were going to take as they walked into this place, then she took the opportunity away to randomly assign their treatments. Therefore, she went from doing an experiment to just an observational study. So she happened to observe that her kickboxing students had more stress relief or stress level reduction than her yoga ones, but that doesn't mean it's because they took the kickboxing class. It just happened to be they were related together. And so remember, our studies cannot show cause and effect. So all she's done here is shown a correlation. All she's shown here is a strong relationship, but she's not actually proven that kickboxing reduces the stress level of her students, more than yoga would. And the reason is because these confounding variables, these lurking variables, have snuck into her observational study, and she's completely either unaware of them or forgotten to reduce them by spreading them out. So a possible issue with her observational study or this example altogether is people who choose kickboxing, if they volunteer to choose it, over yoga might just be more intense and stress people to begin with. So therefore they have more stress to lose at the end of the course. That's a possible confounding variable that she completely forgot to address in this observational study. So before she goes and claims that kickboxing is the solution to all your stressful needs, she would have to understand that she didn't really prove that. She just happened to see a strong correlation between the two. So instead, what could she have done differently to determine which activity is better at relieving the stress? So this is the next question on the back. What she should have done is randomly assign those volunteers to one of the two classes rather than letting them select on their own which course they wanted. This may not have been something that was possible. All right. So this may have been something that she didn't want to scare customers away by saying, hey, welcome, you're doing kickboxing. So instead, her motivation would have been more trying to make sure she's making money by allowing people to choose which course they want, which is perfectly fine. There's nothing wrong with that. But then she can't claim it as an experiment. So in order for her to do an experiment, maybe what she would do is say, hey, I need 40 volunteers. I will randomly assign you one of my two courses, and we will see what your stress is. If it comes at them at that kind of initial situation, they might be more willing to decide or be willing, I guess, to take either class that they're given versus having their choice. So we got to remember, in order for it to be an experiment, in order for it to show causation, in order for us to say A does actually make B happen, then we would have to randomly assign our treatments. Letting people select their treatments on their own is not going to prove that. All right, another example in your notes. An article from the USA Today reports the number of victims of violent crimes per 1,000 people. It says 51 of the victims have never been married, 42 are divorced or separated, 13 are married, and 8 are widowed. Is this an experiment? Why or why not? Well, again, look through your example here. Do you see anywhere where it has claimed that these people were randomly assigned to be the victim of a violent crime? I would certainly hope not. And the answer is no, we do not see that in there. So no treatment was imposed on these people. It just happened to them by random, or not by random, but just, it was their turn, the situation they're in. So we can't say that, victims of violent crime are, unmarried people. And in order to avoid becoming a victim of violent crime, you should be married. Like that would be a bad claim to make based on our example, because we didn't randomly assign different groups of people to be victims of violent crime and see if it happens. So a confounding variable here to be concerned with would be age. Younger people are more at risk to be victims of violent crimes and less likely to be married, divorced, or widowed just because they're younger. That's it. It has nothing to do with your marital status and violent crimes. They just happen to be related based on age. So again, watch for these confounding variables. AP exam writers love to trick you. Make sure that the example actually randomly assigns the treatment. We will trick you on this, so be prepared. All right, example 6. 4 new word processing programs are to be compared by measuring speed with which standard tasks can be completed. So basically typing. 100 volunteers are randomly assigned to one of the 4 programs and their speeds are measured. Is this an experiment? Why or why not? We're going to say yes because what do we notice right here? Volunteers are, and there's our key right here, randomly assigned. Boom. We have our treatment. We have an experiment. Everything is happening like we expect it to. So now that we know this is a good experiment and that this can actually show cause and effect, let's answer these questions. What type of a design did they use? What are their factors and levels? And what will be the response variable to measure success versus failure? So for the design type, remember there are 3. Completely randomized, randomized block, and matched pair. Well, if we look in the prompt, it gives us the information we're looking for. 100 volunteers are randomly assigned, nothing about breaking them into groups, nothing about matching them up with unique characteristics. So option number 1 is our design method here, completely randomized. Just take the 100 people, pull names out of a hat. You got this one, you got this one, and keep going until everybody's been assigned randomly one of the treatments. For the factors, we want to know, what are we asking? What are we trying to answer? What are we going to be looking for? We're going to be measuring the word processing programs. And then for levels, how many different types of word processing programs are we going to be looking at? So we have 1 factor, the processing program, and it has 4 different levels. Program A, program B, program C, program D, or program 1, 2, 3, or 4. Whatever you want to call it, there are 4 different varieties of the factor, which is the word processing program. How will we know for the response variable when the program has been a success or failure? Or how will we know which one is better versus the others? We're going to measure the speed at which the program is able to allow people to complete their standard tasks. So right here, it tells you by measuring the speed. So that is where your response variable comes from. Okay, so that's an example of an actually good, well-written experiment, and then it's designed properly with random treatments and has tested the factors properly and measured the results. All right, continuing with the same example with the 4 new word processors. Again, the 100 volunteers are randomly assigned, so we know it's a good experiment. Is there a potential confounding variable now that we have to be worried about making our claims invalid? The answer now is no, because we've used one of our experimental designs, because we have randomly assigned the treatments with no bias or preference on our part. Then any confounding variables have been completely randomized throughout the process and therefore covered. However, that does not mean we can't improve this design. There are ways to improve it. And one of the ways that I would suggest improving it is this last part right here. If we were to split the participants into blocks based on their initial typing speed, so we all know some people are really fast at typing, some people are okay at typing, and some people are just terrible, like they pick at the keyboard one at a time. If we were to split them up into groups based on their initial skill level, and then within those individual groups assign one of the 4 treatments randomly to people, then we would have a better idea of which program actually works the best, because each program would be tested on people who are really fast, people who are okay, and people who are really, really, really bad. So I would have one of the, all 4 programs would be randomly assigned to the really fast people, and that'd be like its own experiment. All the really, really, or all the really, really slow, unable to type at all people would each also be randomly assigned one of the 4 programs, to where each of the program has one of those. And then lastly, the people right in the middle, and then we'd be able to see which program actually works better, because our final results would be based on the fact that everybody involved had a chance at all of the programs. It takes a little bit more time to set it up that way, but that would be a way to improve it using a randomized block design. And I'm blocking based on initial skill level, because that would be the one that I am, that's the one variable I'm concerned is going to cause the most issue with my final results. I could also block where each person would use each program in a random order, more like a matched paired thing. But there's really no need to have all 100 people try all 4 programs. It would be very tedious. So instead, the better option is this way here. But you could do that if that's something you want to do. All right, I believe this is our last example here, kind of wrapping up the experimental design notes. Suppose that we have a manufacturer who wants to test a new fertilizer against one that is already used on the market. So they have 10 2-acre plots of land scattered throughout this county. So each plot then is subdivided into 2 subplots, one of which is treated with the current fertilizer, and the other half of that plot is going to be treated with the new fertilizer. Wheat is planted and the crop yields are measured. So which type of design is this? So again, this is the hard one, you got to look for it. But if you look, all of your 10-acre plots, or all of your 2-acre plots, all 10 of them were split into 2. So now you have all of these little farmlands spread out across the county that have now been divided into 2 equal parts. And so now you have paired things that are similar. So you're dealing with a matched paired design. So each of the plot lands becomes the experimental units, and you've got the 2 green happy faces, and you get the 2 red sad faces, or your farms, each half of that one plot of 2-acre plot of farm is now like those matched people. And so randomly, the farm is going to be chosen which half gets fertilizer brand new and which half gets fertilizer that's already been used. So matched paired is the design. Not easy to spot. This is going to take you guys some practice doing the homework and looking at these to make sure you know which one you're looking at. The question then becomes, when does the randomization actually occur? Because remember, we have to randomly be assigning some sort of treatment at some sort of process throughout this. And the randomization is going to occur once we split the plot in half. We're going to decide which half randomly gets the new treatment versus the old fertilizer treatment. That's when the randomization happens. So it could be a coin flip. It could be a pull a card out of a hat, whatever, like, you know, number 1, number 2. It's, as long as it's random, it doesn't matter which method you use. So wrapping up this unit, what is the most important thing to take away from some of these experimental designs? Number 1, randomization. We need randomization in all of our experiments in order to eliminate the potential effects of confounding variables. Without randomization, at best, it's a study and it's really not showing any causation. So spreading that uncontrolled confounding variable evenly throughout the treatment group is very important, and randomization guarantees that that is going to happen. Different randomization techniques are better than others, but overall it has to be randomly assigned treatments. Without that, you are dealing with a bad written experiment, and I say at best it's an observational study. Other things that we can use to help our experiments is blocking. Blocking is a way of putting things into groups so that when we go to do our experiment, we're guaranteeing that our treatment is evenly spread out through all of the different characteristics of our experimental units, our rabbits, our people, our farmland, our typing skills, whatever. Typically you block to remove a variable that's going to cause you concern with variability. So variability, remember, is how far apart my data is across the graph. If I run an experiment and I've got data spread out all over the place, I really don't have a good answer to what the final result is of my experiment. So instead, I want to narrow down my variability and make it a lot more concise and precise in the middle of the graph. And we're going to see this when we do our dog activity here the next day or two. Doing that helps reduce our variability. So blocking based on what I'm concerned with takes care of that variability as much as possible. There is another way to reduce variability. So overall variability is not very favored when it comes to your experiments. And that is using a controlled, is by controlling your sample size. Larger sample sizes produce statistics with less variability. Meaning if I do an experiment with 10 people, I might get 10 random results that may or may not tell me the answer. If I do that same experiment with 100 people, I'm going to start to see a trend, all right? Because over and over again, we're going to be repeating it with different characteristics, and we're going to start to see the similar stuff pop up. If I do that same experiment with 1,000 people, even more accurate results. If I do it with 10,000 people, even more accurate results. Sometimes, though, you can't go that high, so you want to be able to use the largest sample size possible. So again, if variability is a concern when you're looking at your experiments or designing them, then larger sample sizes are a way to reduce the variability. Just keep in mind, though, that sample size does not affect the bias. So if you're starting to select people that you think will be more successful at your experiment, then you're still introducing confounding variables and bias. So you need to make sure it's random, random, random. All right, that wraps up the final notes here for the experimental design. There's 2 more examples in your note. I'm just going to kind of read through them, but if you were to actually design one yourself from a prompt, it would look something like this. Now that we've covered all the elements, could we put one together ourselves without having a prompt already for this? And the answer is, yeah, it's not too difficult. So I could give you something like this. You have 60 rabbits, and you're going to test which of the 3 rabbit foods increases sizes the best. So we would explain how to design an experiment with completely randomized design, and then a completely randomized block design. So we're going to show both methods, and then draw the diagram to represent the situation. So something that you might have to do on a test is fill in all those little rectangles that say, you know, experimental units, randomized, what my treatments are, what I'm measuring, and comparing at the end. So an example of that would be for completely randomized, this one here. Go ahead and number those rabbits 1 through 60. Put the numbers 1 through 60 on pieces of paper and put them in a hat. Mix the numbers, randomly select 20 numbers without replacement, and the 20 rabbits with the corresponding numbers are going to get treatment 1. Do the same thing again for the next 20 rabbits, and they're going to get treatment 2, and then the remaining rabbits will get treatment number 3. So basically, again, I'm pulling random numbers out of a hat. Hey, that rabbit number 56, treatment 1. Rabbit number 22, treatment 1, until I get 20 of them, and then do that for treatment 2, and for the leftovers would go to treatment 3. Again, random has to be part of your experiment. If it's not random, randomly assigned treatments, then it's not good. My little rectangles would look like this. So my first rectangle would show my experimental units. So that's my 60 rabbits. My vertical rectangle here says I randomly assign the treatments. I don't have to explain the random process, but it needs to be made aware to the reader that they are randomly assigned. And then just talk about how many are going to receive each one. 20 random rabbits will receive treatment A, 20 are going to receive treatment B, and 20 are going to receive treatment C. We'll measure the growth. So you want to talk about what you're measuring, what's your response variable. So we're going to be measuring growth of each of these and then compare the results at the end. That'll tell us which one was the better rabbit food, A, B, or C. That's it, completely randomized. If I'm concerned that the initial size or gender or breed or age or whatever of the rabbits could be a potential variable that skews my results a little bit, then I can use a randomized block design where I'm going to put rabbits into blocks or groups based on common characteristics. Again, potential choices include the breed of the rabbit, what their size is initially, their age, their gender, whatever. Since I'm testing how much they're going to grow, for me, maybe I'm worried about at the beginning, the bigger rabbits not growing enough or the smaller rabbits not getting enough food or whatever. So I'm going to break them into groups based on their initial size. Keep in mind that blocks need to be similar. So if I'm going to break them up into size, I can't mix and match. All the little ones have to be in one group. All the big ones have to be in one group. All the medium ones have to be in one group, whatever I'm going to do. And I can have 2 groups, 3 groups, 4 groups. There's no minimum requirement. Just make sure your groups are very similar, homogeneous. You want them to match. The blocks don't have to be the same size. So my rabbits don't have to be split equally, 30-30 down the middle, but it helps. We don't want anything like 5 small rabbits and 55 big rabbits, because then the 5 small rabbits are getting more attention than the 55 big rabbits are. So we do want to keep it fairly balanced, but it doesn't have to be exactly the same. So if you got like 29 or 30, that's fine. And then there will be units in each block receiving each of the treatments. So the whole idea of blocking is that your large rabbits will both get rabbit food A, rabbit food B, rabbit food C, and your small rabbits will also all get rabbit food A, rabbit food B, rabbit food C. So we want to make sure the food is used in both blocks. So the description for my randomized block looks like this. Put the rabbits into blocks based on their size. The 30 largest will be in one block and the 30 smallest will be in the second block. So I broke them into 2 groups, 30 largest, 30 smallest. We will number the treatments 1, 2, or 3. We're going to put 10 ones in a hat, 10 twos in a hat, and 10 threes in a hat. So of my 30 largest rabbits, 10 of them are getting the first rabbit food, 10 are getting the second rabbit food, and 10 will get the remaining rabbit food. For each rabbit in the block, select 1 slip of paper without replacement, and then that's the food that they're going to get. That's the way I decided to do it this time. Again, compare everything within the group first, and then you can compare everything overall. So it's basically now 2 experiments in one, 2 randomized experiments in one. So I have my initial 60 rabbits for my experimental units. I broke them up small and large in their own group. Then I randomly assigned them A, B, and C. So this time 10 get A, 10 get B, 10 get C. Measure the growth of each of those groups, and then compare the treatments for the small rabbits. Do the same thing for the big ones, 10 get A, 10 get B, 10 get C. Measure their growth, compare the treatments for both rabbits. Maybe I notice in each group, like A is the best here and B is the best here. Maybe I notice A is the best in both of them, whatever. I'm going to compare separately first, then compare the treatments for all the rabbits in general. So I can come to a final conclusion and say A worked great with both groups, A is the best food. Or if you have a small rabbit, I would use C because it worked better, but if you have a big rabbit, I would use B. Whatever the results are, we can be able to say that if we keep it separate at first, and then we can put it together at the end. All righty, guys, that is it for the notes on experimental design. If you need any more help with anything, again, make sure you're asking during class after we're done with our lessons. We'll do our dog activity to explain this more hands-on in detail, but that is it for today. Look forward to seeing you guys in class. Let me know if you got any questions.